Day 28, Honors Physics, Projectiles, problem number 35. Here's a good problem because I guess the way I would word this is that this requires some industrial strength algebra on this problem. So that's a little bit more fun than just doing your basic algebra. Let me show you what I mean by that. So I have my diagram of the rock being thrown off a cliff into some water. Release point A, B is impact point with the water, 60 meters from the base of the cliff, and a 30-meter high cliff. So I will then start with my component diagram, but in this case it will be an expressional relationship because I don't know all the numbers specifically. In other words, I don't know V. I know the angle. So V is the actual vector. Then we have V sub x, the x component, and V sub y, the y component. So the cosine of 40 is V sub x over V. So V sub x is equal to V, the actual velocity, times the cosine of 40. So that's an expression for the horizontal velocity in terms of the actual velocity V. That's V sub x then. So V is the overall velocity. And then V sub y, correspondingly, is V sine 40. So V sine 40 is an expression for the y velocity, which will change throughout the problem. This will not change. The V cosine 40 is a constant, but that doesn't really even matter at this point per se. So then I go to my normal setup for my horizontal and vertical components. So my x component is V cosine 40. So I just got that from down there on the bottom. And my initial vertical velocity is V sine 40. My horizontal displacement upon impact at point B will be 60 meters. Didn't put the M on there. And my vertical displacement will be negative 30 meters. It's going to fall 30 meters. And the acceleration is always negative 9.8. So now we have some, what you might consider messy algebra, but just a little bit more technical, a little bit more maybe advanced, or you got to be a little bit more determined to get through all the algebra here. Let me pause this for a second. Okay, so this probably magically appeared on the screen, but here's what I did. This is a generic equation for the relationship between, well, the velocity, the constant velocity is displacement over time for a horizontal, well, something moving with constant velocity, V equals S over T. That's just generic. In this particular case, my V sub x is V cosine 40. My horizontal displacement will be 60 meters. That's a 60 there. That's 6D, 60, over T. The one thing that connects this problem is the T is going to be the same for both vertical and horizontal. Anyways, I have an equation here, well, with two unknowns. Now, once again, here's our third uniform acceleration equation in generic form. My displacement vertically, that's not horizontal, that's a vertical S. You can call it S sub y if you want, but it's the vertical. Is going to be negative 30. V sub I is, if you can see this, is V sine 40. That's, I plugged this right here, the V sine 40, in for the V sub I right there. And then I have my T plus the 1/2, and the acceleration 9.8. Actually, I forgot to put the negative on there. Shoot. So you have to put a negative in there. I was trying to squeeze this in. Let me try to do it. I don't know if I can get it in there. I'll put it with a black. So that 9.8 right there is negative. Negative 9.8. That's important that I have that negative. Just notice that. And then your T squared. All right, so now we have two simultaneous equations that have a V and a T in them. So this is solvable using algebra. What I would do, and I have this more laid out on a written piece of paper that I gave you on Friday, or I gave it to you in class someday this past week. But I probably would take this equation right here, solve for T. Well, let me do that. So I've rearranged this equation, solve for T. T will be 60 over V cosine 40. So what I would do in this problem, I'm going to let you figure it out because you guys are pretty good at algebra. You will take this quantity here and you will plug it in for T right there, and you will plug it in for T squared over here. So you got to make sure you square it over there. That's a little bit tricky. But then work through the algebra. And once you've done that, plugging it in, the only thing left will be V. You can solve that for V. V will be the actual answer to part A. And then once you have V solved algebraically like that, then you can just take that V that you just solved for and plug it in right here for this V to get the time, which is the part B of the problem, the time of flight. But part C of this problem, you got to sort of start over. You got to figure out how high this rock goes. So you will have to do a little bit of a reset. I'll let you figure that part out. Bottom line is to get, I'll just label the diagram for a second. I'm going to call this, I'll call it point C up here at the top. This is say at the pinnacle, how high it goes off the water level. So what you have to do now is start the problem sort of over. You got to go back to your vertical components in order to do part C. You will have to reset these. Although now you will know this number because you'll have V, so you'll actually know this even for part C of the problem. I'm picking my launch spot A and my final spot point C. This will be a known number now, and this will be negative 9.8 still. And your V final at the top spot will be 0. And once you do that, you can figure out S, which will be then not negative 30 in that case. It will be a number more than positive 30 because it'll be higher than 30 meters off the water level. But bottom line is you'll know this number, V sub F, vertically will be 0 at point C, the pinnacle, and just solve for S to do part C of the problem. All right, go to it. Have some confidence. You can do this.